Hello dear friend, myself Prof. Sukhbarujki. Today we learn new topic radiation. In radiation we discuss some important concept in chapter 3rd. Firstly we discuss kinetic theory of gases and another part is a radiation. Here we can discuss some important concept. First one is a coefficient of a absorption. First definition, coefficient of a absorption. It is defined as the ratio of quantity of radiated energy absorbed by body in a given time to the quantity of radiated energy incident on the body in the same time. In formula, this definition we can write here coefficient of absorption. Here coefficient of absorption is considered A, and the quantity of radiated energy absorbed by body in a given time. Suppose this consider as q suffix a, and q be the quantity of radiated energy incident on the body in the same time. Then formula become here a is equal to q suffix a upon a be the coefficient of a absorption. Coefficient of absorption is also called absorptivity or absorptance. Absorptance. It has no unit and dimension because two quantity are same here. Another definition, coefficient of reflection. Second definition, coefficient of reflection. It is defined as the ratio of quantity of radiated energy reflected by the body in a given time to the quantity of radiated energy incident on the body in the same time. Mathematically, we can written in this way: coefficient of reflection denoted by small r, q suffix a, q suffix r. Here q suffix r be the quantity of radiated energy reflected by the body in a given time, and q be the radiated energy, the quantity of radiated energy incident on the body in the same time. Then we can write here coefficient of reflection denoted by small r. R is equal to q suffix r upon q. It is also called reflectivity or reflectance. It is also called what? Reflectivity or reflectance. It is also no units and dimension because both quantity in a same here. And third definition is a coefficient of a transmission. Coefficient of a transmission definition same here. It is defined as the ratio of the quantity of radiated energy transmitted through the body in a given time to the quantity of radiated energy incident on the body in the same time. Here coefficient of transmission denoted by small t, and q suffix t be the quantity of the radiated energy transmitted through the body in a given time, and q be the quantity of radiated energy incident on the body in the same time. Then coefficient of transmission denoted by small t is equal to q upon q suffix t upon q. It is also called transmittivity or also called transmittance. It is also has no unit and dimension. Here we conclude that coefficient of absorption, coefficient of reflection, coefficient of transmission, it has no units and dimension. Then we can discuss here uh, another concept is the relation between relation between coefficient of absorption, coefficient of reflection, and coefficient of transmission. Here to show that here show that a plus r plus t is equal to 1. Right, we can prove here. Q be the quantity of radiated energy incident, q suffix a quantity of radiated energy absorbed, q suffix r quantity of radiated energy reflected, and third one q suffix t quantity of radiated energy transmitted. According to law of conservation of energy, this total energy, this become q is equal to q suffix a plus q suffix r plus q suffix t. Then dividing by q throughout here, then here q upon q is equal to q suffix a upon q plus q suffix r upon q plus q suffix t upon q. Here q gets cancelled here, remaining 1 here. Then q suffix a upon q is a here, coefficient of absorption. Q suffix r upon q is a coefficient of reflection, and q suffix t upon q, it is also called coefficient of a transmission. Hence we can written here 1 is equal to a plus r plus t, and therefore a plus r plus t is equal to 1 here. Here ask some question here. Define the following term. First one is a coefficient of absorption, coefficient of reflection, and coefficient of transmission, and also show that a plus r plus t is equal to 1. Our question here, define coefficient of absorption, reflection, and transmission, derive the relation between them. Then another important concept is perfectly black body. Perfectly black body. Firstly, we discuss here definition of a perfectly black body. Definition: a body which absorbs all radiated energy incident on it is called perfectly black body. Definition repeat here: a body which absorbs all the radiated energy incident on it is called perfectly black body. For perfectly black body, absorption A is equal to 1 here, small r, coefficient of reflection is 0, and coefficient of transmission is also 0 here. Hence this body is called as a perfectly black body. According to Ferry black body, here given Ferry black body. Firstly, we discuss here construction and working. For practice purpose, lamp black A is equal to 0.98. 0.98 is treated as a natural perfectly black body. According to Ferry black body, firstly we discuss here construction. It is an artificial black body which consists of an double wall, here double wall hollow metal sphere having a small aperture. Here is a small aperture given here, and the inner surface of the sphere is coated with lamp black, and outer this surface, consider here, the inner surface of the sphere is coated with lamp black, and outer surface is polish. This outer surface is polish. Outer surface is polish, is nickel. It has conical projection. Here is a conical projection uh, diametrically opposite to the aperture. Here is a conical pendulum and aperture be the opposite to each other. The space between the two wall evacuated to avoid loss of heat by conduction and convection. How to working in a Ferry black body? The radiated heat enter the sphere through the aperture in this way. Aperture, the radiated heat entering the sphere, suffering here multiple reflection. In each reflection 98% radiated heat is absorbed. So after a large number of reflection, almost all the radiated heat is absorbed by the sphere. Effective area of a perfectly black body is equal to the area of aperture. Some question asked on this topic: define perfectly black body. How can it be released in a practice? Or another question asks, what is perfectly black body? Explain the construction and working of a Ferry black body with the help of neat label diagram. Or another question is, with a neat label diagram, explain Ferry perfectly black body. And another one, next topic is a emissive power. Definition. Emissive power definition here: emissive power of a body at a given temperature is defined as the quantity of radiated energy emitted by the body per unit time per unit surface area of the body at that temperature. Emissive, or repeat again definition: emissive power of a body at a given temperature, it is defined as the quantity of radiated energy emitted by the body per unit time per unit surface area of the body at that temperature. This emissive power denoted by here capital E. Then quantity of radiated energy emitted by the body is Q. Unit surface area is capital A, and T be the temperature. Then emissive power given by here E is equal to Q upon AT. Here Q be the quantity of radiated energy emitted, A be the surface area of the body, and small t be the time, and capital T be the temperature. Next one is a absorptive power. Absorptive power of a body at a given temperature is defined as the amount of radiated energy absorbed per unit time per unit area by surface at a constant temperature. Here some question asked on this topic: state SI unit and dimension of emissive power and coefficient of emission. Then emissive power, SI unit of emissive power is a joule per meter square or watt per meter square. Dimension here uh, here dimension m raised to 1, l raised to 0, t raised to minus 3, and another one coefficient of emission, there has no unit and no dimension, hence coefficient of emission is unitless or dimensionless. Then another one is uh, uh, emissive power of a body depend upon following factors. Here emissive power of a body depend upon following factor. First factor is a temperature, another factor is the nature of the body, and third one surface area of the body, and last one nature of the surrounding. And another one is a coefficient of a emission. Coefficient of a emission, we prepare definition of coefficient of absorption, coefficient of reflection, coefficient of transmission, and another one is a coefficient of a emission. Definition we can prepare here. Coefficient of emission, coefficient of a emission of the body, the ratio of emissive power of the body at a given temperature to the emissive power of a perfectly black body at the same temperature. The value of coefficient of emission of perfectly black body is a 1. This is a very important. The value of coefficient of emission of perfectly black body is 1. Then coefficient of emission is denoted by E. Then formula become here small e is equal to capital E upon E suffix b. And next point is a Kirchhof law of radiation. Kirchhof law of radiation. Statement. It states that the coefficient of absorption of a body is equal to the its coefficient of a emission at any given temperature. That is, coefficient of absorption is equal to coefficient of a emission. Here we can write here A is equal to E. Then theoretical proof of a Kirchhoff law. Consider a large enclosure which is thermally isolated from the surrounding. Then this enclosure is a constant temperature enclosure. Consider an ordinary body. Suppose this ordinary body, consider O, and perfectly black body, here consider B, of the same surface are placed in the given enclosure. Okay, then we consider here, let the emissive power of ordinary body, consider capital A. Emissive power of absorption of ordinary body, consider A. And another one, coefficient of emission of ordinary body, coefficient of emission of ordinary body, consider small e. And emissive power of perfectly black body is E suffix b. Surface area of each body is equal to capital A here. Both the body will attain a same temperature by thermal exchange. Then suppose Q be the radiated energy incident per unit time, per unit area of each body. Then we can write here the total energy incident on a body, capital B, per unit time is AQ. Okay, total radiated energy incident on body B per unit time is given by here A into Q. The total energy absorbed by the body, capital B, per unit time, here become AQ, that is a coefficient of absorption of a black body is a 1. Then total energy emitted by the body, capital B, per unit area, suppose this become A capital A into E suffix B. Therefore The temperature of body capital B is a constant. Therefore, we can write here the energy absorbed per unit time is equal to radiated radiated per unit time. Energy absorbed per unit time is equal to energy radiated per unit time. Then we can write here A into E suffix B is equal to AQ. Here A gets cancelled, remaining hot, E suffix B is equal to Q. Consider equation first. The total radiated energy incident of ordinary body per unit time, Q is equal to AQ here. Total radiated energy incident on ordinary body per unit time, O is equal to AQ. Then radiated energy absorbed by the ordinary body Q per unit time, this become A into small a into capital A into Q here. Then radiated energy emitted by ordinary body per unit time, this become A into E. Therefore, temperature of body O is constant. O is a constant. Therefore, radiated energy emitted per unit time, radiated energy absorbed per unit time here. Here, radiated energy emitted per unit time is equal to radiated energy absorbed per unit time. Therefore, we can write here radiated energy emitted per unit time is equal to radiated energy absorbed per unit time. Therefore, we can written as A small a into capital A into Q is equal to A. Here A gets cancelled, remaining hot E is equal to small a into Q. Consider equation second. Then dividing equation second by equation first here we get E upon E suffix B is equal to small a into Q upon Q. Here Q gets cancelled, remaining hot E upon E suffix B is equal to A, but E upon E suffix B is equal to E. Therefore, we can write here A is equal to E, that is coefficient of absorption is equal to coefficient of emission. This is a Kirchhoff law. Okay, this is a Kirchhoff law. Some question asked on this topic. State Kirchhoff law of radiation and give its theoretical proof. Repeat question. State Kirchhoff law of radiation and give its theoretical proof. And next one, Wien's displacement law. Wien's displacement law. This is a very important statement. The wavelength for which emissive power of a black body is maximum is inversely proportional to the absolute temperature. Wien's displacement law. The wavelength for which emissive power of a black body is maximum is inversely proportional to the absolute temperature of the black body. Mathematically, we can written here This is a When's displacement law, that is uh, lambda max directly proportional to 1 upon t, that is lambda max inversely proportional to the t, or lambda max uh, inversely proportional to t. Here lambda max into t is equal to small b, where b is uh, where small b be the When's constant and its value is 2.897 into 10 raised to minus 3 meter per Kelvin here. Basically, this law is useful in determining temperature of a distinct star, sun, moons, etc. You might have heard of hot dwarfs and red giants. White dwarf are hot star with a surface temperature nearly equal to 10,000 Kelvin, while red giants are cooler, corresponding to the surface temperature nearly equal to 3000 Kelvin. Some question asked on this topic: state When's displacement law. Another one is a question is lambda max, the wavelength of corresponding to the maximum intensity for the sun. It is the blue green region of a visible spectrum. Why does the sun then appear yellow to us? Okay, answer is the wavelength of blue green light are shorter wavelength. These color are scattered out by the earth atmosphere. Thus the time the radiation from the sun reaches our eyes, we can sense only the longer wavelength. As a result, it's appear yellow to us here. And another one, Stefan-Boltzmann radiation. Another point is a Stefan-Boltzmann law of a radiation. Statement: the rate of emission of radiation energy per unit area, or the power radiated per unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. Statement: repeat here, the rate of emission of radiated energy per unit area, or the power radiated per unit area of a perfectly black body is directly proportional to the fourth power of a absolute temperature. Here given some Stefan constant is equal to sigma is equal to sigma is equal to 5.67 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. And SI unit, this given by here value of Stefan constant is 6 point here sigma is equal to 5.67 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. SI unit of Stefan constant is joule per meter square per second per Kelvin raised to 4. In this way, and a dimension of a Stefan constant is given here, L raised to 0, m raised to 1, t raised to minus 3, and k raised to minus 4. Then another one, expression for the rate of loss of heat by black body in a cooler surrounding. Suppose that black body of a surface area, consider capital A, and absolute temperature capital T is kept in a cooler surrounding which is at a lower absolute temperature. Suppose this lower absolute temperature is considered T0. If Q be the amount of radiated energy emitted in time, suppose this time considers small t by perfectly black body, then from the Stefan's law, heat radiated by the body per unit time per unit area is equal to q upon a into t here. Q upon a into t here is equal to sigma or sigma into t raised to 4 here. Heat radiated by the body per unit time per unit area q upon at is equal to sigma into t raised to 4. Then energy absorbed from the surrounding per unit area per unit time, this become sigma t raised to 0 raised to 4. Therefore net loss of energy by perfectly black body per unit area per unit time is given by here sigma into t raised to 4 minus sigma into t raised to 0 raised to 4. Here take sigma common here, sigma into t raised to 4 minus t raised to t suffix 0 raised to 4. If the body is not perfectly black, then net loss of energy per unit area per unit time, this become E into sigma into t raised to 4 minus t suffix 0 raised to 4 here. Okay. Then question also on this topic, state Stefan-Boltzmann law. Next one is what is the value of Stefan constant, and state its SI unit and dimension. And another one, how is the expression modify if the body is not black, or using Stefan's law obtain the expression for the rate of loss of heat by a black body in the cooler surrounding. How is the expression modify if the body is not black? Okay. Here if the body is at temperature lower than the surrounding, that is here if the body is at temperature lower than the surrounding, that is T less than T raised to 0, then this equation become E into sigma into T suffix 0 raised to 4 minus T raised to 4 will be the net gain in the thermal energy of the body per unit area per unit time and last one is a spectral distribution of a black body. Last point is a spectral distribution of a black body radiation. See this diagram. Here the rate of emission per unit area per unit, here the rate of emission per unit area or power per unit area of a surface is defined as a function of a wavelength lambda of the emitted radiation. Scientific study the energy distribution of the black body radiation as a function of a wavelength. Here given graph here, radiated power versus wavelength. This wavelength consider here nanometers. Okay, by keeping the source of radiation such as cavity radiator at different temperature, they measure the radiated power corresponding to the different wavelength. The measurement were represented graphically in the form of curve showing variation of the radiated power per unit area as a function of a wavelength lambda at different constant temperature as shown in this figure here. k shown in this figure here. In this way we can complete here spectral distribution of a black body. Here we complete chapter number 3rd, kinetic theory of gases, in first part, and another one is a radiation. Today we stop here. Thank you.